Hello everyone, welcome back to the Science Data Science YouTube channel. As I promised in the morning, I will come live and share with you how you can fix the problem of overfitting and multicollinearity using your Python, right? So let's start. Let me share my screen. Here we go. All right. Okay. So in the morning, I have introduced you with the most common problems that happen with you. Might be like it is happening right now. Your model get overfitted or it has a multicollinearity issues, right? In the regression model, this is the most common problem. Either you are a beginner or you are a fresher. This video is going to help everyone, so stay with me till the end of the video and watch it how you can fix this problem if you are facing it right now, or maybe you can, if you are not working with the regression model, then it will help you to understand about the regression common problems and how you can fix it. So let's start. So what is multicollinearity in regression models? Like when, let's say you have a 5 features in your data set, you have a one target feature. If we take an example of simple your house sale price, right? So the sale price is your the target one, but there are other features available, independent features. Those are your number of rooms, area of the house, near to bus stop, near to school, right? These are the independent features. So maybe they are strongly connected with each other, highly correlated, the independent features. That is called multicollinearity. If it happens in your data set or in your model, then it is not good for your model health. You have to fix it. Okay. So there are three solutions to this one. You can use the VIF. This is variance inflation factor. We use this is an inbuilt Python method. You can import the library, you can apply on your data set, and you can check with the values of VIF factor if they are highly correlated with each other, the independent one, right? The second solution is your ridge regression. This is we also use to reduce the overfitting as well. I will show you in the next, like the cell. First we will talk about the first problem, and then you have the apply PCA to remove any high correlated feature from your given data set. Okay, so let's start. So first of all, we will discuss about the VIF method. So I have imported the libraries. This is NumPy, Pandas, Matplotlib, Seaborn, Stats model. Okay, so this is we are going to use. You need to import it if you want to use VIF method. Okay, because that method is a part of these stat models library. Okay, and then you have a SK linear model, linear regression, because we want to use the ridge regularization method as well to reduce the multicollinearity. I will explain in the upcoming cells like how it is going to help you. Okay. Stats model, outliers influence, import variation inflation factor. This is what you are going to use to fix your this problem, multicollinearity. Okay. What it will do, if there is a multicollinearity, it causes the your inflated standard errors, and it will also cause the unreliable predictions which we don't want, right? So here we go. So I have taken the small data set. This is the, we have generate the synthetic data. This is x1 first feature, x2 is the second feature, and x3 is the third feature. So here the correlated with the x1. So your x2 is highly correlated with the x1, and your x3 is less correlated with the x1. This is just for your like the knowledge, but I will show you by checking as well. So here I'm using the df.core method as well. If you want, you can use right? It will also give you some statistical idea about the your each feature exists in your data set. Here you can see x1, x2, x3, and this is your target, and it is showing the correlation diagonally. This is 100% because every feature is highly correlated with itself. But it is also showing the x1 is correlation with the x2, this is one, and with the x3 this is correlated with the your x2 in positive, like the correlation, right, 17%, and with the target this one, and with the x3 this is negative correlation. Okay, now we will look at the heat map as well. Look at this. This is the result of heat map. So here you can also look for the correlation between the each feature. On the right side, this is the bar. The your darker the red color, this means highly correlated. Lighter the color, here is a less correlated. And if this is the negative correlation. Okay. In this, there are three type of correlation: positive, negative, no relation. Okay. Now here we look at the x1 again. This is 0.05 and it is correlated with your this one 0.18. Okay. And with the x3, this is negative. Okay. And same with the x2, you can check like this way and so on. Okay. So these are the just additional method I have added if you want to check the correlation. But I will show you now the exact like the method if you really interested to check the multicollinearity before building your model. Okay, this is a good habit, so your model will not like have these kind of problems when you are applying the algorithm on it. Okay, here we go. So now we will separate the your independent feature, and because we don't apply your here multicollinearity solutions to the dependent feature, because our goal is to check the correlation between the independent feature. We are not talking about here the target feature, so we will not use that. We will separate our independent features using this pandas method, and then we will declare use an instance of your stat model dot add constant of x. So why we are adding this constant in this? The reason is because when you are going to check the here collinearity between your independent feature, we will set some here intercept value. Okay, it is not going to be affect your in here your inflated like this stand your variations in the feature. It is just for to understand the model from where it can start, right, the value using as an intercept and check the correlation between each independent feature. This is only the purpose. So if I'm using the sm add underscore constant, by default it will add once for each your intercept value of the given feature. This is only the purpose, nothing else. And then we will create the data frame, your VIF underscore data, and then we are just here separating the feature VIF feature. We will create this x dot columns. So what are the columns? These one, right? And then we are using here list comprehension. Look at this. So here this is the your inbuilt method variation, sorry, variance underscore inflation underscore factor, which you have imported here. Okay, so now we will use this one, and we will say of x dot values. So what are the x dot values? Whatever the x dot, this means each feature's coefficient value. Okay, because now your VIF will try to predict if they are highly correlated with each other based on their coefficient value. And of I, for I in range x dot shape of 1. This is just we are just running over the how many features we have coefficients, and it will run the loop and it will show you this output. Right now we are not doing anything. I'm just trying to show you the VIF values, because we are just detecting if there is any multicollinearity between the your independent feature. Now look at the result. So this is your constant value it added. Okay, this is the VIF value of your constant coefficient intercept, and then this is the your VIF value for your first feature, This is the VIF value for the second feature, and this is for the third one. Now it is clearly showing you the first two feature is almost like close the VIF value, right? So this means they are highly correlated and we cannot ignore it. Okay, so you can see this is the best way to check the multicollinearity using VIF. It is giving you the very clear vision how you can check it, and now you will be able to decide which feature you are going to drop to fix it, because this is only the solution. Okay, now how we will do that? We will remove the x2 from your this feature. Okay, here you will fix df x1 x3. We will remove it from the feature in simple way, and then we will add your constant intercept, again the intercept value to this data frame. Okay, and then we will create the new data frame, and now this is your result. Okay, now you can use these features only to put into your model, to train your model. This does not contain your multicollinearity. If you will use, you can do the experiment using this by applying the model. If you are using any house sale prediction data, maybe you have any other data, stock market price or any other data, right? You can apply it with this method as well and without this method as well, and check the performance of the model, and then it will make you, give you the very like the good understanding at a deeper level. Okay, so this is just the experiment, right? But this is the just your like the solution to handle your multicollinearity. Okay, this is one of the solution, and now we will move ahead with the next solution. This is your ridge regression method to handle multicollinearity. Okay, so ridge regression I have also shared in my regression, like the algorithms why we use it. Okay, in detail. Ridge regression, it will shrink the value of your coefficients. So what is coefficients? The weight you are assigning to each your feature. Based on that, it creates the relationship between your features, right? And then it will create the linear relationship between the target and the other feature. So ridge will help us to reduce or shrink the value of the coefficients and try to move towards the zero. Because if your coefficient value or like of your each feature to going towards the zero, this means it is going close to the mean, right? And it is not going to occur any errors, right? And your model predict correct value. This is the goal of ridge regression. Okay, technically, like at the back end or mathematically. Okay, so now look at this one. We call it to adding the penalty value as well. Okay, in other terms. So here we will again import this one. If you have already imported above, you don't need to import it again. And then we are again creating the random data here, and this is your we are creating one feature which is highly correlated with the x1. This is why this is the target variable. Okay, so you don't need to create this dummy data. This is my purpose is to show you that like how you can apply this. You can use your real data here. Okay, and then we will create the data frame. First of all, we will train a regular linear regression model. Okay, this is your ordinary least square method, OLS. This is the most baseline model we use to check the like the coefficients value and check the relationship of the features. So we are going to apply here. So here, before upfitting onto the model, we need to separate the independent dependent feature. So that's why this is X, this is Y, and we are fitting onto this. And now we will train a ridge regression model using our ridge model, right? This is a solution. So here I have declared the instance of ridge model ridge alpha is equals to 1.0. What is this? This is the penalty value we are adding in each coefficient, right? So we can reduce or shrink the coefficient value. Okay, so it can be any value. You can try with the different value. You can start with the 0.001, then 0.1, then 00, your 0.02, something like that. You can compare with the different values. I'm using the default one, right? You can try the range as well. Here, the most important thing I would like to add, the one tip here, whenever you are using the ridge or either lasso regression, this is another regularization method. Whenever you are setting the alpha value, you need to take care of one thing in your mind. Don't try to use the high penalty too much. Okay, what happened in that case? It will shrink your, like, the coefficient value or feature. It will take it towards the mean value. But what will happen in that scenario? In some cases, if you are pushing your all data points more or become zero, okay, in using ridge regression it is not going to be zero, okay, it will close to zero. But using the lasso regression it will become sometimes zero, and it remove the irrelevant feature as well. In that case, sometime what happen, by adding the large penalty, your model may get biased. It will not be overfitted, but it may get biased. Okay, so whenever you are applying these methods, please keep in your mind these kind of the things. Don't apply in a rush. Just think about it, check the performance of the model, keep change the value, and then use the best one. Okay, and here you have the, now we will print the coefficients of this one. Now look at this. This is your standard, like the basic, your OLS ordinary least square model. This is 1.6, 3.4. Okay, but if you look at this one, this is, you can check it now, this is 1.8 and this is 3.24. Okay, so it shrink little bit this one, but this is not, right? So it depend upon the functionality, but alpha value we are giving, right? And then we are plotting the here your graph as well. So to show you the difference between the coefficient value of your x1 and x2 as well. Okay, so here in this scenario, if you look at this one, now your highly correlated feature, the x1 was, you are with this one, x1, x2. If you look at this value now, it is if you have applied this one, right, 3.4, 1.6, it seems to be correlated, not too much, right? And then if we look at this value, this is very far away from now, so it is trying to reduce the relationship between your both x1, x2. Okay, and now we will move on to the next value. This is your PCA method to handle multicollinearity. This is the next third method, very popular. In this, you need to import here your PCA library, SQL from the sklearn package, decomposition, import PCA, right? Principal component, your this one, because it help us to reduce the dimensionality of your features, data, right? Again, we will create the here dummy data. We have a here three features and one dependent feature. Now again, we will check the multicollinearity here using VIF. This is the first step. Again, you will add some constant value here, and then you will create the data frame here. Here we are just separating the your this is the same method we applied above, right? We are separating independent feature, creating the data frame, then we will apply the variance inflation method, factor one, and check the value of each of VIF. So we come to know which features are highly correlated. Is x1 x2 related, is x2 x3 are related, or x1 x3 are related, right? So now look at this. This is your constant value. Your again x1, x2 are highly correlated. Okay. So now we will apply the PCA. So here you will create the instance of PCA and number of components you set to. Okay. You can set to 3 as well. It depend upon, we already have the 3 features. So I set it to. If you have a 10 features, 20 features, you can set it up to 3 as well. It depend upon your requirement. Okay. PCA will also help you. What it will do? It will not pick up your all elements like x1, x2, x3. It will give you the combination of most of the the values from your all features and create only two features which you can use to train your model. Okay, so here we have a pca dot fit underscore transform. We will use it. The most important thing when you are applying the PCA, you have to scale your data. This is very important. Okay, and after scaling, then only apply the PCA on your features. Okay, here we are just applying the now linear regression model. Now look at this one. So this will like reduce your three features to the two principal component. So in this PC1 contains the maximum, like the you can say uh, value which helps your model to understand the relationship between the features. It contains the maximum of the data, and PC2 contains the 30% of the data, but your PC1 contains more than 60% of your data. Okay, now this is also very useful, and now there is a no multicollinearity. You can check here the PCA component value as well. Okay, this is a coefficient value weight, this is the maximum, this is a 3.04. Okay, so these were the three different most popular method if there is a multicollinearity in your data set, and you can fix it like this way. Okay, now we will move ahead to your problem 2, that is overfitting and underfitting. This is also very important. Okay, overfitting, I have seen, maybe you also heard when you start learning the machine learning, right? These are the very common words, you terms you heard, right? Is your model overfitted, is your model underfitting, right? How will you fix it, right? Because if your model is overfitted, only the thing is it will work very good, great, you will be very happy because it is going to give you the very good accuracy, maybe above 90% on your training data. But again, you feel hurt when it will give you the less than 60% or maybe more less than that on the test data. Reason, because when your model overfitted, it does not like learn the actual pattern or relationship between the feature. It learn from the noise actually. Okay, so it is not able to predict the things correctly when we pass the test data to your machine. This is a problem. And underfitting, this is opposite. It will not understand the relationship between your feature. Okay, if I have already explained it like in a very simple way, as a with the layman example in my shorts. I will share that link in the description box if you want to go at a deeper level for the overfitting and underfitting. The solution to these one is L1, L2 regularization method. L2 method you have already seen. This is ridge, this is lasso. And then you can also use the feature selection to reduce the overfitting. You can try the polynomial regression if it is not a linear relationship. Linear, this means like when you draw, here I will show you, look at this. So this is the linear relationship. If you, this is the x, your x variable, this is y target, and this is the trend line. Okay, so this is a clear relationship, the line is going like this way. Okay, in case there is a no linear relationship, in that scenario what will happen, I will show you. Here we go. Okay, in that scenario your linear relationship will be something like this, like this. Okay, this will be like your, not the straight line, it will be curve. Okay, this is called non-linear, and we can use in that scenario polynomial regression if model is overfitted. Okay, ensure enough training data to generalize well, this is we can use for underfitting. So now let's start. So you need to import ridge, lasso, linear regression, standard scalar, polynomial feature. We also need to split the data before we are applying any feature engineering application method, and mean squared error just to check the the correct predictions value between difference between the predicted and actual values, percentage. And then there is a make regression, this is for the data set we are downloading. Here we are generating the again x and y make regression. number of sample 2, feature, number of features, noise, and this one. Okay. And then we are splitting the data into X train, Y test, X test, using the test size 20%. Random state 42, this is the journal we use. There is a no technical reason behind it. If you want to use any number, you can. But this is the, if you want to read about it, why we are using 42 only every time, then you can go to the Hitchker, like Hitchker article. This is very popular article. You will find it why we are using it. Okay. And the test size we have set 20% of your total data, right? Now we will scale the data. This is, I told you, you have to scale, right? Either you are applying PCA or you have a regression model. When you are working with the numerical data, you need to scale the data. Okay, this is very important. And then you need to here fit onto the X train scaled data and X test scaled data. Okay, so we are transforming. Now see the difference here. You are fitting and transform the data on the train data, but don't try to fit on test data. Why? I don't want my test data to know the answers. Okay, I don't want to train it before I ask any question or passing the new test data, so my machine will give me the correct result in test cases as well. So we never fit the scaled data on the test. We always fit and transform only on the training data. This is the most important point. Sometimes students fit on both. In that scenario, the test data 20% which you have kept, you want to hide it from the model, right? So you can give later on the actual value so it can predict correctly, right? But if you fit it here as well, what will happen? Your model already know all answers, right? So it will perform well both on. But tomorrow when you come up with the new data which was not here, then your model will fail. We don't want to scale it. Okay. And then apply the polynomial regression. The first method you can use polynomial feature to reduce your overfitting. Okay. You can use the degree 3, you can use the degree 1, 2, this is your choice. And then fit and transform. Then we will transform the test data as well with the poly instance from the your polynomial features. And then I have applied the base model as well. Linear regression, this is the very easy. We are just fitting the linear regression. And then we are fitting the ridge regression. This is, I have already explained about. This is the lasso. So what is the difference between ridge and lasso? Ridge will try to shrink the coefficient value towards the zero, but lasso will make the some your values feature coefficient value zero, and it will also remove the irrelevant features as well. So whenever you are using it, use it wisely, because if you are removing the features too much with the high value, right, and with the high penalty terms, your model may get biased. You will save it from overfitted, but it will make it biased. Okay. And then we will like predict all values of these three. Why I am applying all these three or like the models? Because I wanted to show the difference between all three. And you can use any method. It is not mandatory for you to use all methods. My goal is to tell you all methods together. Okay. And then we are just checking the MSCE accuracy value as well. Sorry, this is not accuracy. This is just to give you the percentage of the difference between predicted and actual values. Okay. And then so we can figure it out. Look at this result. This is MSC for linear regression. There is a no regularization. Look at this 440.85. And for the ridge regression, this is 440.12. This is reduced, right? And lasso, this is more reduced. So this means your ridge lasso regression is working more good, because your lower the value of your here in this 439.99, right? So this means your model was predicted your values more correctly rather than you are using this one MSC, right? Because it is giving us the actual value, difference between the actual value and the predicted one. Okay, so this is not overfitted. I will pick up, you can pick up a like which one is a better, right? But for me, lasso regression model is working more better than the other two. Okay, and now look at this result. So this is the yellow one. The yellow line is going till here. Look at this. And then the red one is here, right? And the green one is starting from here, it is going here. Okay, so this is the blue dots are your original data. So this is fitted more towards, right? And this is the way how you can check, apply the different models, and like how you can choose which model is going to be work best in case there is a overfitting. Okay, and for the MSCE, this is we just can compare the value with the target one. You can take the average of your target variable, right? Check out the value. Let's say I will give you very good example. If you have the house sale price, right? The average value of your house sale price is 100K, and your MSC value comes around under 95K, right? 97K. Let's suppose for this one, right? 97K. So this means this is more closest to your average value, closest to mean. So this is going to be good. If it is showing like the very far away, let's say 60, 65 in other two models, right? So this is very far away. Okay. So this is the way how we do the comparison. And you can also see the here lasso your coefficients value as well. Okay, so that's why you should go with according to by checking the values of MSC as well and your lasso coefficients as well. So here it is not showing any like the relationship between your these coefficient values, right? They are very far away from each other. So this was like all about how you can handle the most common two problems. Tomorrow I will share with more two problems and tell you the solution how you can fix it. Okay, this was from the day one. Only for the underfitting you can create the method smooth. Okay, if it is underfitting you need to add the more synthetic data into your data. If you have a you found the more data, then that's great. If you don't have, you can add the more synthetic data by using the smooth method. I will show you tomorrow in one of more problem where I'm going to use the smooth method, so you will know how you can do that. Basically we use also when we have a imbalanced data. In that scenario your model either go underfit or biased. Okay, underfitting also happen if you are applying the very complex model on the simple data set. Okay, and it is also happen with the overfitting as well. So this comes in both scenario. Okay, so you need to take care when you are going to apply the models on your data set. You have to be very like the you need to take a very wisely this decision when you are going to apply the your models on the data set. Okay, and thank you so much for watching this. If you are new to my channel, don't forget to subscribe my channel. See you in the next live session. Thank you.